In section 5.5 we learn how to use proportions for solving geometric applications. And so in the first part we use this for similar triangles, and then we use proportions to find lengths in pairs or figures that differ only in size. First, let's look at what's meant by similar triangles. So when triangles have the same shape but are of different sizes, then we can say that the corresponding sides of the triangles have the same ratio. That is, the following proportion is true. A to D, these are the similar sides, equals B to E, the hypotenuse in this case, equals C to F. Again, it's important to make sure that what's in the numerator is consistent with one triangle, and then what's in the denominator is consistent with the other triangle. But these are similar triangles, and that means similar triangles have sides where they have the same ratio. So that's important to understand when we work with ratios and proportions for triangles. So let's jump into an example here. So we are told that this pair of triangles is similar. Find the missing length x. So we can say, all right, x to 20 is equal to 9, and 9 is this side, so it must be 9 to 12. Again, x to 20 equals 9 to 12. Then we simply take the cross products. X times 12 equals 20 times 9. Then we divide both sides by 12. So that x is equal to 9 times 20, or 180, divided by 12, and that is equal to 15. So x has length 15. In the next example, we ask, how high is a flagpole that casts a 45-foot shadow at the same time that a 5.5-foot woman casts a 10-foot shadow? Again, we're using proportions, just as we did in example number 1. So we say that the height of this triangle, x, to the height of this triangle here, to 5.5, equals 45 to 10. Again, the vertical x, the height x to 5.5 is the same as 45 to 10. So we cross multiply. So 10x equals 5.5 times 45. We divide by 10 on both sides. So x equals 5.5 times 45 divided by 10, and that is equal to 24.75. So in other words, the flagpole is 24.75 feet high. In number 4, we are told that the sides of the photographs below are proportional. So that's important. Right triangles are similar, but for rectangles, you have to say that to apply the principle of proportionality, you have to say that the sides are proportional. Find the width of the larger photograph. So the width of the larger photograph is X centimeters, and the width of the smaller photograph is 6 centimeters. So again, we use proportion, and that's X to 6 centimeters. Yeah, the width of the larger photograph to the width of the smaller photograph is equal to the length of the larger photograph, 35, to the length of the smaller photograph, to 10. So here we have the larger and the smaller. So whenever you set up these proportions, it's important to keep in mind what's in the numerator, what's in the denominator. Obviously, it has to be consistent, otherwise this isn't going to work. So we cross multiply, and we get 10x equals 6 times 35. We divide both sides by 10, so x equals 6 times 35 divided by 10. And that is equal to 21. So we can state that the width of the larger photograph is 21 centimeters. And again, it's really, really important when we have application problems that we state the correct units of measure in our final answer. As you notice, when it comes to units of length, we've used centimeters and feet and inches. So be very clear what your unit of measure is, especially in your final answer. That's unambiguous. For the next example, we look at a model of a skylight. And so here's a model with width of 3 centimeters and a length of 12 centimeters, versus the real one being 52 feet long and has a width of W feet. So we start out by saying, okay, let W be the width of an actual skylight, W here. Now we use a proportion of 12 to 52. So in other words, this is the model to actual. Again, it's important to keep straight what's in the numerator, what's in the denominator. So the actual, we have the W here, and so we want the model part would be equal to 3 centimeters. So we cross multiply, 12W, or W times 12, equals 52 times 3. In other words, W would equal 13. So the width of an actual skylight will be 13 feet. And I might add that the model is measured in centimeters and the actual is measured in feet. So we have the correct units of measure. So again, the actual calculations are pretty straightforward, but the tricky part is to set this up properly in terms of what is the model, what's the actual, what are the units of measure for the model, what are the units of the actual. And so the calculations are pretty easy. So in this example, to measure the height of a hill, a string is attached. The string is stretched from level ground to the top of the hill. So level from G to the top of the hill. A 3-foot stick is placed under the string, touching it at point P, a distance of 5 feet from point G. So we know this distance here, and we know the height of the stick. And then the string is then detached and found to be 120 feet long. So we know this is 120 feet. How high is the hill? Well, we're looking at similar triangles here. Here's one triangle, the smaller triangle, and here's the larger triangle. And they're similar because they have the same angles here and here. In other words, they have 90-degree angles here and there, and they have a common angle here, therefore these angles are also the same. Again, you don't need to know all the details, but you can see that these are similar triangles. So we can use a simple proportion. So let us set up the proportion. The height of the larger triangle is h, and the height of the smaller triangle is 3 feet. And then the hypotenuse of the larger triangle is 120, and the hypotenuse of the smaller triangle is 5 feet. So this is for the larger triangle, and this is for the smaller triangle. And here all the units are the same, they're all measured in feet. And again, we cross multiply, so we have 5 times h equals 3 times 120. We divide by 5 on both sides, so h is equal to 3 times 120 divided by 5, and that's equal to 72. So we can say the hill is 72 feet high. Again, units of measure are critical in application problems. I would highly recommend you do additional practice problems from the book, and also in my math lab, in the study plan. And so whenever you can do word problems, it will help you understand these problems much, much better. And if you do 20 or 30 of these application problems, you'll be very, very good at it. So that's my recommendation. I know it takes a little time, and but you can certainly handle it. And the more you do it, the easier it will be for you. This concludes section 5.5 and also chapter 5 itself.